Yeah, thank you very much, Ehud. Thank you very much, Jordan. The next mission is an ultraviolet mission, again, a joint collaboration between Israel and the United States. It's a proposal for a mission, and the scientist who's going to present it is Professor Wokesman. He already spoke yesterday, and I'm sure you remember that he is a member of the Weizmann Institute of Science, a very well-known scientist in several areas, theoretical area of astronomy, neutrino physics, cosmic rays, and more. And I'm very pleased with many other people that he decided that theory is not enough and it's time to build a real satellite to measure what he is proposing. So Eli, please come and introduce this mission.
Okay, I think I had an excellent introduction to this talk by the previous two speakers. Even if we don't agree on everything, we agree on the important things, so that's the important part. Okay, so I will talk about Ultrasat, which is a joint Israeli-US proposal for a mini satellite that would carry a very wide field UV telescope. The science mission is led by Weizmann-Caltech collaboration. Our industry partners are IAI, ELOP, and JPL. And the work on this project has been supported by ISA and NASA for some years now. The main goal of Ultrasat is to study transient astrophysical events. Transients are some sort of explosive astrophysical events, and the study of such transients is taking center stage now because of two reasons. First, these explosions are usually quite interesting scientifically, and I will say a few words about this in a minute. And secondly, the technology now enables one to build very wide field instruments that are required for catching these transients for the brief time they are visible on the sky. So these developments drive the construction of large-scale ground-based transient surveys. The leading one is LSST. Also large-scale ground-based radio surveys like LOFAR and SKA. And space detectors, wide-field X-ray and gamma ray detectors. And the last two talks were discussing very wide-field X-ray and gamma ray detectors in space. The UV band is missing from this game. And that's quite unfortunate because explosions are usually very hot at the early phases, and the UV is a good place to look at. And Ultrasat is going to close this gap. The specifications of the telescope are given in this table. The main points are that Ultrasat would have a very wide field of view, 250 square degrees, and it would have a sensitivity that would be better than the best preceding UV space telescope so far, which is GALEX. So Ultrasat will have, okay, I hope that you can see, Ultrasat will have a survey volume for transients, which is 300 times larger than GALEX had. It would have a survey volume which is several tens larger than any current optical transient survey telescopes. And it would have a comparable survey volume to LSST, which is the largest ground-based project for these transients, which should come online sometime around 2022. And of course, Ultrasat would be complementary because it would operate in a different band, in the UV, and it would have access to very short timescales, minute timescale, which would not be accessible for ground-based telescopes. So with this very large jump in capabilities, we would be able to do a wide range of science, astrophysics science topics, and to answer key open questions in quite a few fields. Our Ultrasat group is focused on two key questions. One is the sources of gravitational waves, and the other is the evolution and explosion of massive stars. However, Ultrasat's data would be available in real time to the scientific community alerts would be disseminated in real time to the entire community. And other groups interested in other topics would be able to do their science. I would mention a few. Measuring tidal disruption events of stars by supermassive black holes in the centers of galaxies, measure the properties of variable stars and active galactic nuclei, and so on. So I will discuss in this presentation only the first topic, which is the counterparts to gravitational waves. And this has been discussed quite in detail in the previous two talks. I will just say a few words related to the importance of the UV here. So we would be interested in events involving the mergers of neutron stars, binary neutron stars. Neutron stars are the dead stellar remnants of the evolution of some massive stars with masses of about 1 solar mass and a radius which is only 10 kilometers. The densities inside them, 10 to the 14 grams per cubic centimeter, are nuclear densities, meaning that this is the density inside the nuclei of heavy atoms. Tight binaries of neutron stars, so binaries rotating around each other with an orbit of less than about 1 million kilometers, lose energy by gravitational waves at a rate that would lead to merger on a timescale which is smaller than the age of the universe. So such systems would eventually merge, and they would produce a large signal of gravitational waves that we've discussed yesterday and that was detected only last year by LIGO for the first time. And this, in the long run, with multiple events, would enable us to test the fundamental principles of general relativity. The other interesting aspects of these mergers are related to the fact that part of the neutron star material is torn out of the system and ejected at large speeds during the merger process. And this material is highly rich in neutrons, and it is also highly radioactive. We believe that this ejection of material is responsible for the production of at least part of the heavy elements on Earth, those heavier than iron, and possibly all the way up to the heaviest elements we measure, like gold and platinum. Finally, if we are able to observe these events, we will be able to test the properties of matter under extreme conditions at densities which are close to nuclear densities, which are not accessible to studies in laboratories on Earth. Okay, the importance of detecting the electromagnetic signal was already mentioned by the previous speakers. I would emphasize that it is important to detect the signal in order to determine whether indeed these are the sources of heavy nuclei on Earth, and also to determine the properties of matter at nuclear densities, but also in order to determine the exact distance. As was mentioned before, gravitational waves do not provide an accurate distance and direction to the source, and in order to determine the exact distance, we need to identify the galaxy that hosts the binary that merged. And in order to do that, we need to detect the electromagnetic emission from these objects, because this would allow us to pinpoint towards the galaxy hosting the event. Now, if we are able to do this, we will be able to measure the exact distance, and therefore also to have an independent measurement of all other measurements that we have so far for the expansion rate of the universe. And with a large number of mergers, we will be able to determine this expansion rate quite accurately. What's the advantage of a UV satellite that we are discussing in this game? So starting 2021, we expect the improved gravitational wave detectors to provide detections of such events at a rate of roughly once per month, with directional accuracy of about an error box of about 100 square degrees. And these events should be coming from distances of about 600 million light years. Ultrasat will be able to access more than half of the sky at any given time, all the directions away from the sun. And it would be able to identify the electromagnetic emission from these objects in a time scale of few minutes, because the field of view of Ultrasat would be containing the entire error box of the gravitational wave direction. Detecting such distant events in other wavebands is going to be challenging. They could be accompanied by bright X-ray and gamma ray emission, but this would happen only to a fraction of the events. And detection in radio and infrared is going to be very difficult because it's going to be late and faint. The recent detection of the neutron star merger by LIGO last year sort of confirmed the picture that I've just shown you. The LIGO detector provided a fairly large error box, but because the event was fairly near on cosmological scales, it was possible for ground-based telescope to go one galaxy after another to search for the electromagnetic counterpart until a counterpart was indeed detected. As you see, a new source appearing in this before and after picture next to the center of a nearby elliptical galaxy. The emission was extremely hot. Although it was detected only 10 hours after the event, it was still above 10,000 degrees Kelvin, which implies that most of the emission was in the UV. The emission was much brighter than we expected, at least 3 times brighter, which implies that we would see not only all the events triggered by LIGO, but we will be able to see these events to much larger distances, and we will detect about 10 to 15 events per year not triggered by the gravitational wave detectors. This would enable us to point the gravitational wave detectors to search for signals in their data in the correct direction and time, and to expand the horizon of the gravitational wave detectors. In addition, it would enable us to do a more systematic study of these systems at larger distances and at all inclinations, because the gravitational wave detectors would not be sensitive to some of these events if they have the wrong inclination with respect to the direction to Earth. Finally, indeed, this event was extremely bright in the UV, as we hope it would be, and it was quite faint in other wavelengths, which implies that for large fractions of these events which are far away from us, it would be quite difficult to detect the counterparts in other wavebands. I'll skip this for time. A word about the implementation. So Ultrasat is essentially a wide-field UV telescope, 0.5 meter diameter mirror with a 30-centimeter aperture. It has at its heart a UV camera with a very sensitive UV CCD detector, which reaches a quantum efficiency of about 70%. The satellite is built around the telescope. It's small and light. The volume is less than 1 meter cubed. The mass is about 150 kilograms. And these small mass and dimensions enable us to have a hosted launch accompanying the launch of a big, much bigger communication satellite to a geosynchronous orbit or to the geo-graveyard orbit, which is a bit higher. And this combination enables us to build this entire project, including the launch and operation, for the cost of about $100 million, which is, as you know, extremely cheap in these games. So, Ultrasat will be the first wide-field UV transient survey. It would have a survey volume which is 300 times larger than the best previous UV telescope. It would have a survey volume which is comparable to the largest ground-based optical transient project which is being constructed and hopefully will start operating in 2022. And it would operate in a different band and would be sensitive to much shorter timescales than the ground-based telescopes would be. With this very large improvement in capabilities, Ultrasat would have a major impact on many open questions in astrophysics related to explosive astrophysical events, like the nature of supernova, tidal disruption events, of stars by supermassive black holes, and others. One of our key science goals would be the detection of electromagnetic emission from the sources of gravitational waves, mainly binaries involving the mergers of neutron stars. And we will be able to see such events to extremely large distances beyond the horizon of the gravitational wave detectors, and therefore improve the science output of those detectors. And finally, you get all this for a very small mass, size, and cost satellite. So if you have some additional $10 million to chip in, yeah, we need $10 million from each of these guys to complete the mission. Okay, thank you.